Factors that affect solubility. So there's a lot of things that can affect solubility, just like when we were doing acids and bases, there's a lot of things that can affect the pH in an equilibrium problem. And so the factors that can affect solubility, I'm going to talk about each one of these individually, but these are the four, okay? Besides like heating it up. We know if you heat something, generally you're going to make it more soluble. I'm not talking about that because heat changes the temperature, which will change the K value. So I'm not talking about that right now. I'm talking about other ways to affect solubility. So you can have what's called a common ion. So if I was putting in calcium fluoride into something and there was already fluoride in there, that is considered a common ion. So common ion would be ion in solution and the compound that you're dissolving. Okay, it is the same ion. And that's going to shift the equilibrium, okay? It's like adding in a product that's part of that dissociation equation. So it's going to shift the equilibrium, okay? If I put some in, so if I'm looking at here, let's write this. Say it's AB solid, those two, A plus and B minus, right? If I added in a common ion, maybe some more B minus, that's going to make it shift this way. So it's going to shift left and be less soluble. Okay, so if there's a common ion in there, it's going to be less soluble. And we're going to talk about that more in detail in a minute. I can also change the pH. When we looked at the iron hydroxide in the previous video dissolving, it affected the pH. So if I change the pH by adding an acid or a base, that is also going to affect solubility. Okay, so right, I change the pH. That can add H plus or OH minus. Actually, let's do add or remove. H plus or OH minus, that's going to affect the solubility. Now, this one is more like chapter 24. I think we will talk about this later. But some ions, especially metals, can make what are called complex ions. And essentially, it's just using an ion that was in my equilibrium to make something else. So if it's used in a second equation, that's like taking it out of the equation. So if this was my thing again, AB makes A plus plus B minus, and maybe I'm going to use this to make a new complex ion. That would be like taking out some of the B minus. So that's going to make it shift this way to fill in the space, right? According to Le Chatelier's principle. Okay, so a new complex ion formation essentially is making something else. And it's usually something kind of complex. So like I said, we'll talk about that more in detail in chapter 24. And the last thing is something is amphoteric. Remember, ampho means both. Things that are amphoteric can act like an acid or a base. So we have to kind of look at which way it's going to dissolve and how that's going to affect pH and things like that. All right, so I'm going to go into each of these individually a little bit more in depth. First, we're going to start with a common ion. Okay, if I add a common ion, again, ion in the solution and the compound, okay, so if it's the same ion, it's going to reduce solubility. Okay, right, just like what I said above, essentially it's just a Le Chatelier's thing. If I add in some B minus, it's going to shift it to the left, so make more solid, so it's actually going to be less soluble. We are going to test this in the lab. You should get it to be less soluble if you have a common ion in it already. Okay, so for example, if I add NaCl to lead chloride, remember this guy isn't very soluble, what would be my common ion? Okay, well, chloride, right? Chloride is in both of them. That is the common ion. So if I'm looking at my solubility of PbCl2, right, it's not very soluble. So we got this whole equilibrium thing going on, Cl minus. If I add in some Cl minus, it's going to shift it to the left. So let's say I increase this. It's going to cause it to shift this way, and it's going to be less soluble. So this is all Le Chatelier's principle, which we learned about in the equilibrium unit, right? It will shift to reduce the stress. Okay, essentially, it wants to get back to the equilibrium values, right? So it shifts left in this case, making it less soluble. Okay, so that's all based on Le Chatelier's principle. Okay, so we're going to put some numbers to this. I got example number 4. What is the molar solubility? Okay, remember molar solubility is X. I'm looking for X of calcium fluoride. We did this one in the previous video, CaF2, in a solution that is 0.020 molar NaF. So how do I do this mathematically? Well, my common ion right here is going to be fluoride. Okay. Now, anything with sodium is completely soluble. So essentially, this is the amount of F that I'm adding in. Okay. If you check your solubility rules, usually we'll put it with sodium because anything with sodium is soluble. So this means my common ion is fluoride. I am already going to have 0.020 molar fluoride in there. So I'm wondering about CaF2. So that's what I should be writing my equation for. Okay. So I've got CaF2 solid. I get Ca2 plus and 2F minus. Okay. Now, this is where my ice table is going to be a little bit different. If I already have fluoride in there, that affects my equilibrium. So I don't care about that. I already have fluorine. So instead of putting 0 there, I actually already have 0.020 molar fluoride. Okay. So if I have that, the common ion amount goes in the initial spot. Now I didn't have a common ion of calcium. Hey, it's still going to be plus X and plus 2X, X. This one though is not just 2X, it's 0.020 plus 2X. Okay, so if I were to write my K expression for this, it's going to be X times this plus 2X squared. Now, this algebra looks a little bit more complicated, right? Now, I have KSP from that previous problem. From example number 1, it was 3.4 times 10 to the negative 11th. This is from example number 1. Okay, so I have that. Now, you're welcome to use the solver button if you want to, but just like in our acid and base equilibrium, these K values are so small that anything that is like plus X minus X, you can drop and then solve for X because it's actually not going to make that much of a difference. So I can drop this. So instead of doing this, and like I said, you're welcome to use your solver, I would just do X times 0.020 squared equals 3.4 times 10 to the negative 11. And I get that X is 8.50 times 10 to the negative 8th molar, right? This is our ice tables, and that is actually what I am looking for. Now, see what I mean by it being so small, 8.5 times 10 to the negative 8th. That's a very, very tiny number, just not very soluble. And so if I were to plug that back in, it's actually not going to change the K value like at all. So this is very, very small. So it doesn't really affect much. Doesn't affect this concentration because I started with 0.020, which is a lot more than this value. Okay. So like I said, solver is fine, or you can drop anything that is plus X or minus X essentially. Okay. Now, I said this makes it less soluble, right? Anytime you have a common ion. So let's check that. All right, I'm going to compare this to my example number 1. And in example number 1, we got that X was 2 times 10 to the negative 4th. That was how soluble it was. And in this example, we have 8.5 times 10 to the negative 8th. It's almost twice, 2 times more soluble in example number 1 than it is here. This is really not very soluble. And the reason being, I already have a bunch of F minus in here, so not very much more can solve. Okay, so it affected the solubility. All right. Okay, so that was the first type, common ion. Now we're going to